Let me get started. I will introduce our today's speaker to our audience first. Dr. Chong is a PhD candidate in the Computer Science Department at the University of California, Santa Barbara. His research interests include machine learning and AI for science, with emphasis on global optimization, bandits, active learning, and experimental design. He's an editorial board reviewer of GMLR, serves on PC of several conferences, including AAAI, ASDEX, SML, KDE, and NeurIPS. Part of his research has been deployed at Amazon, which is a remarkable achievement. Let's hugely welcome Dr. Liu to give us today's talk, Global Optimization and Parametric Function Approximation. Hi, Chong, please go ahead.
Okay, thank you. Thank you for the very nice introduction. The title of my presentation is Global Optimization with Parametric Function Approximation. And this is a very recent work on arXiv preprint, and feel free to check it out. So this is the outline. I'd like to go over the problem statements and then move to the key idea, the algorithm, the regret analysis, and then the experiments and ongoing and future work. First, black box optimization is everywhere. For example, in material design, material scientists, they want to generate some material and they need to carefully choose different processing parameters. For example, the temperature and the pressure, and it goes through some black box chemistry process to generate the material. And it is very similarly in the drug discovery. And also in the robot planning, let's say here is a cleaning robot. The robot needs to make the decision, take the action to walk around your house. And the whole optimization goal is that do the cleaning of your house. And also in the game, you play with your friends. That is a optimization that the final reward is that you want to win, right? And also in the drone flights, let's say the drone is going to deliver something. The optimization problem is that how to fly the minimum time to deliver the food to someone. And also the black box optimization may exist in making a coffee. I'd like to take the coffee, for example. This is me, and right now I have a very fancy coffee machine. What do I need to do? First, I need to choose the different coffee beans. Is that a Robusta coffee bean or Arabica coffee bean? And I need to choose a milk. Is this a whole milk or reduced fat milk or low fat milk? And also I need to choose the pressure of the water. How many bars of the pressure I need to put on the water to go through the coffee machine. And finally, also the steaming time of the milk. I call this is my decision set. I take this decision and then go through the coffee machine and make a coffee for me. And I can test the coffee and rate the tasty score of this coffee. For example, let's say right now that is 1 to 10. I can give the score between 1 to 10. I call this process is called observe some rewards. By observing the new reward and what I need to do is to update my decision. And this whole process runs in iterations. But the problem is that I can only enjoy up to 2 cups of coffee every day. And here is a key question. The key question is how to find the best way to make the coffee within the minimum days. So this is the example of the black box optimization in making the coffee. Also, the black box optimization may exist in hyperparameter tuning. Let's say right now, here is a computer scientist, and they want to tune the different hyperparameters of the deep neural network. For example, the learning rate, the batch size, and the number of iterations. The whole process looks like, first, they train the deep neural network on the training sets using the decision set, including your choice of the learning rate, batch size, and the number of iterations. And you make some predictions. You make predictions on the validation sets and then observe the validation accuracy. Of course, the hyperparameter tuning is one to maximize the validation accuracy. And after observing the validation accuracy, the computer scientist will update the decision sets. And this whole process also runs in iterations. But the problem is that, as this paper points out, the hyperparameter tuning is very expensive. For example, it usually takes about 14 days to do the ImageNet 1K training. If you want to do the training within 90 epochs, ResNet 50, NVIDIA M40 GPU, and in totally, I mean, it includes 10 to the power of 18 single precision operations, which is very, very expensive. Just to ignore the number of operations, I mean, in terms of time, it needs 2 weeks, right? And here is a key question. The key question is, how can we do small number of training to find the best set of the hyperparameters such that it maximizes the validation accuracy, right? This is the goal of the hyperparameter tuning. I'd like to do a small summary here. This is the framework of the black box optimization. You can understand that this is the game between the player and the environment. And I'd like to use the hyperparameter tuning as an example to walk you through this process. So every time the player at time 1 takes the action, and I call this action, this is x1. And in this example, the x1 can be the learning rate equal to 0.01, batch size, that is 24, number of iterations to be 200, right? And the environment, which is the hyperparameter tuning deep neural network, will release a reward to the player. That is y1. What is y1 in this example? That is a validation accuracy equal to 89%. And then the player take another action. I call it x2. X2 in this example is learning rate is equal to 0.001, batch size that is equal to 20, and the number of iterations to be 250. And the new reward in this example, I call it Y2. Y2 is validation accuracy that is equal to 92%. And this whole process is able to continue, right? That is X3, and then I have Y3, and this game can play until sometime. This is the framework of the black box optimization. And there are 2 key challenges of the black box optimization. The first challenge is that to observe the rewards, it usually involves a lot of time or the computational cost or the human efforts. For example, in the making a coffee example, right? I need to, physically make the coffee by myself every day. And in the hyperparameter tuning example, it takes about 14 days for the ImageNet 1K training, for one training. And also, another challenge is that there are no results of unselected actions, which is really bad. For example, in the hyperparameter tuning, if you do not take the action, that is learning rates equal to 0.01, batch size to be 24, and the number of iterations to be 200, then you will have no validation accuracy of this set, of this unselected action. So overall, the goal is that, the key question is that, how can we take few actions to find the action that maximize the reward? And let's move to the problem setup. Right now, I have the black box function, which I call it fx. And my goal is that I want to find the x star such that it is able to maximize the fx. Here, the f is a black box function. What does it mean? It means that I have no information about, is it a linear function or nonlinear function? I don't know. Also, I have no information about, is this a convex function or non-convex function? I don't know. Also, I have no information about the gradients, which means that I cannot use a linear function optimization, convex function optimization, or first order, second order gradient optimization methods to solve this kind of problem. But fortunately, we do have some observations. It is denoted by YT. It means that every time I query a data point at xt, here's a fxt, that is a true function value at xt, and my observation is noisy. Here's a eta t, it means a noise. This is the independent zero mean and the sub-Gaussian noise, which is like the standard and noise modeling that we usually see. So at time 1, I or the player query a data point at x1 and then observe y1. At time 2, the player query at x2 when the observe y2, and then x3, y3 until some time. So in this whole process, I'd like to define the cumulative regret as an evaluation metric, which is defined as follows. This is the summation over the suboptimal gap. I'd like to use a one-dimensional example to help you understand the definition. So here I have 6 observed data points. And the red line, which means the maximum function value according to the max over x of the true function fx. And all the suboptimal gap are denoted in blue. I mean, they are the summation over all these 6 suboptimal gap. And clearly, it is compared with respect to the maximum function value, which means that the cumulative regret is the smaller, the better. There are some existing approach to solve this kind of problem. For example, a naive way is that we like to do the uniform query, which means that every time at time t, I'd like to select the xt by uniform distribution over the function domain. For example, in this one-dimensional example, I can randomly, by the uniform distribution, select the 6 number of data points. And then I can run some regression on these observations to get my estimated function. I can do the argmax over the estimated function and then output some x hat as my output. But the problem is that it does not take the function structure into consideration, which is bad because you can run the uniform query for any function without considering the function structure. There is a line of successful research called the Bayesian optimization. That is use the active query method. And the model, the key idea is that they assume the true function f is drawn from some Gaussian process, and they rely on the Gaussian process prior, Gaussian process posterior to update the belief of the model, and then do the active query. But the clear drawback is that, in theory, it suffers from the curse of dimensionality. What does it mean? It means that in practice, it usually performs badly in high dimensions. And in terms of the hyperparameter tuning example, it means that Bayesian optimization is not good if there are too many hyperparameters that needs to be tuned. And the key idea of my research of this project is that, okay, we still interested in the global black box optimization. And the key question here is that how can we work well in the high dimensions? We know something about the deep neural network, right? We know it is strong. And the key idea is that why not we use a deep neural network to approximate the black box function? Every time when we observe something, every time we observe the output of my queries, and then I can update my model of the deep neural network and then use it to optimize the black box function. So this is the key idea of this work. It does not assume the Gaussian process assumption as in the Bayesian optimization, but the key idea is that we'd like to use a deep neural network to approximate the black box function and then do the optimization. This is the key idea. Before moving to the algorithm design, I'd like to introduce a very key realizable assumption here, which is standard, I should say, in the bandit setting and also maybe in the reinforcement learning. It says that right now I have a parametric function, which can be a deep neural network. And I have the parameter set. The parameter set includes all the parameters that is able to use with this deep neural network. Every parameter in this set, for example, this is W1, it is able to describe a function that is f hat W1. Here the f hat is my model, is my deep neural network. And I have another W2. I have the model f hat, right? And the W2 is able to describe another function, f hat W2. The realizable assumption says that there exists optimal parameter W star within my parameter set, such that the model parameterized by the W star is equal to the true function, is equal to the true black box function. So in this figure, the red box is my model, is my deep neural network. It says that there exists a best parameter W star that is equivalent to the black box true function. But I want to say that the W star is unknown. That is something we need to estimate. And by using this assumption, by approximating the true black box function, the problem reduces to approximating the best parameter W star. So this is the introduction of the realizable assumption and how the problem is reduced to be the parameter estimation. This is my algorithm. It is called the global optimization with upper confidence bound. I like to call it the GoUCB algorithm. And it has two phases. In phase one, I'm doing uniform query. And in phase two, I'm doing active query. In phase one, after uniform query, small n number of data points, I'd like to run some regression on all the history data that I collected, and then I can estimate some parameter W0 hat. The goal of phase one is that I'd like to make sure my estimated parameter is somehow close to the best parameter W star. And the goal of phase two is that I'd like to refine my estimation to be some better estimation that is even closer to the best parameter W star. For example, here in phase two, at time one, I have W1 hat that is closer to the W star. And then at another time, I have W2 hats that is even closer to the best parameter W star. So this is like the overview of the design. There are two phases of the algorithm. And in the next slide, I'd like to dive deep into the phase two design. The phase two design runs in iterations. It runs from the time one to time big T. And first of all, I'd like to run some regression on the all history data that I collected. Please pay attention here. The history data means that from time one to time T minus one, which means that it did include all the history data from the very first time. And then the key step, that is step two, I'd like to build the parameter uncertainty set. I call it ball T. And the ball T, it is centered at WT hat. What is the WT hat? WT hat, this is the output of the first step, right? It is my newly estimated parameter. And this is the center of the ball T. The key design point of the ball T is that it must contain the best parameter with high probability. Why? Because if the ball T does not, or the ball T is not able to capture the best parameter, then the algorithm will always behave very, very differently from the best parameter W star, which means that the algorithm will behave differently from the true function, which is bad. So the ball T must contain the best parameter. And here I'd like to highlight again, the W star is unknown, but with some algorithm design, we can make sure the ball T contain W star with high probability. And in the next step, I'd like to select XT, which is cross optimization over the X. Here the X is the argument, the function input, and also another max over the W. W is a parameter. The W optimization is contained within the ball T. So the max over the X, the max over the W in the ball T, I usually call it the optimistic exploration. What does it mean? It means that I am optimizing, I am searching in the parameter space towards the optimal parameter W star. I'm doing optimization and I know whatever I like to choose, the best parameter always performs the best because it is able to maximize the function. And by doing the max, I have some W. And if it is close to W star, then it's good. If it is not close to W star, what I can do is that I can still update the ball by shrinking the size of the ball, by reducing the number of the parameters of the ball, such that the W star is also contained in the next ball, in the updated ball. And also I do the argmax over the X. This is also the optimistic exploration. It is searching over the input space. It is searching over the function domain. By the cross optimization over the X and the W, this is what I should say, the optimization under the uncertainty towards the best solution of the black box optimization. And finally, by choosing this XT, I observe the YT, that is the true function value at XT plus some noise. So this is the detailed design of the phase 2, which is the active query part of the Go UCB algorithm. So here comes the cumulative regress bound of the Go UCB. It says that, okay, under the realizable assumption, which I introduced before, this is the key assumption, and also other thumb mild assumption, the cumulative regress of this algorithm is at the order of the square root of T. What does it mean? It means that if I do the uniform sampling over the outputs of all the X1 until the X big T, the big T here is the total time horizon. And it means that the rate of the convergence to the optimal point, that is over the rate 1 over square root of T. How can I achieve this? Please pay attention. Here is a E of the convergence bound. Here the expectation is taken over the uniform distribution, and the first term, that is max over the X, that is Fx, stay the same because that is a maximum value, right? And in contrast, in the Bayesian optimization, if the Bayesian optimization is working with the merging kernel, and here is a cumulative regress bound, and also doing the uniform sampling over the outputs over X1 until X big T, the rate of the convergence to the optimal point, that is something like the T to the power of V minus V over 2V plus D squared. Here, the V is something like the constant that is able to describe the margin kernel, but please pay attention here. The small d, this is the dimension of the inputs. In the hyperparameter tuning example, The D means the number of the hyperparameters that we'd like to play with. For example, here, let's say the D is 10, and the D square means 100, which means that the Bayesian optimization usually converges much slower than the Go UCB, which is bad. But which means that the Go UCB is better than the Bayesian optimization in theory. And also I have the experiments. I'd like to choose my parametric model to be a neural network with 2 linear layers, where the dimension of the activation function is 25. So here is the structure of the 2 linear layer neural network. The first linear layer, and then after that, I choose a sigmoid activation function, and then another linear layer. The idea is that, okay, the F hat is my model, and it is used to approximate the black box true function. So this is the experimental setup of the experiments. And first, I'd like to show something about the synthetic experiments. Remember, our goal is that I'd like to find the X star that is able to maximize the true black box function fx. And here I have 3 synthetic tests. The first true function, the first black box function, f1, is created by setting all the numbers in the parameters of the model to be 1, which means that here f1 is equal to f hat w. Here the w is just all the 1 numbers. It includes all the weights and also bias of the linear layers of the neural network. And the second experiment, the black box function, that is 20 high-dimensional Splinsky-Tom function. I'd like to show an illustration of the 2-dimensional Splinsky-Tom function like this. As you can see, it has a global maximizer and 3 local maximizers. The final problem is F3. F3 is a 20-dimensional Rastregian function. Here is an illustration. The illustration shows the 2-dimensional Rastregian function. As you can see, there are many global maximizers, which is very hard to optimize. And this is a synthetic result of all the F1, F2, and F3. Here, the x-axis, that is time horizon. You can understand the time horizon as the number of the iterations of the running of the algorithm. And the y-axis here, that is a cumulative regress. As we discussed before, this is the lower, the better. And the first 4 methods are the Bayesian optimization method. I'd like to highlight the GPUCB, GPEI, GPPI. These are 3 very traditional Bayesian optimization methods. And the trust region Bayesian optimization is relatively state-of-the-art of the Bayesian optimization and also AutoML community. But still, we can see the purple line, that is the Go UCB, that is able to perform the best by having the lowest cumulative regrets. And also, I have the real-world hyperparameter tuning experiments. Here, the problem is that I'd like to find the best set of the hyperparameters that is able to maximize the validation accuracy. And I have 2 tasks. First, I'd like to play with the multi-layer perceptron for some classification task, which includes 8 hyperparameters. And another task is that I play with the gradient boosting, which includes 11 hyperparameters. And here in the first task, here is the example. What are the hyperparameters? It includes your choice of the activation function. It includes your choice of the learning rate and your choice of the different number of the iterations. And the result is quite exciting. Here, I'm doing the experiments on the breast cancer dataset, which is one of the UCI datasets. And also the x-axis here, that is the time horizon, and the y-axis here is cumulative regrets. Remember, the cumulative regrets is lower the better, and also The first four methods are the Bayesian optimization method, and the last one, the purple line, that is my algorithm, that is GoUCB. And we can see that in the first figure and also in the second figure, the GoUCB is able to perform significantly better than the traditional Bayesian optimization method by having the lowest cumulative regrets. Okay, finally, I'd like to talk about something of the ongoing and the future work. The first problem that I'm very interested in, that is called the misspecified GoUCB. It is defined as follows. Remember, I talked about a realizable assumption before, which means that the true function is within the function set. And here, this is the true function f star. And here, this is the function class controlled by the parameter class, the big W. Previously, by saying the realizable assumption, it means that the true function is within the function class. And here, misspecified GoUCB means that there is a clear gap between them. So it can be an interesting and theoretical problem to work with. And by showing this definition, it means that the gap is upper bounded by some epsilon, and the epsilon will goes to your cumulative regret bound if you can successfully solve this kind of problem. And another ongoing and future work is that it is called the multi-fidelity GoUCB. It means that the black box objective function can be approximated by multiple parametric function, f1, f2, until f big M. So what are the differences among these parametric functions? Let's say right now they are sorted, they are pre-arranged, and f1 means that it is easy to compute but has a large approximation error. And the last function, the f, the big M, that is very expensive to compute but has the smallest approximation error. So the key question here is that how can you use this set of different level of the approximation to solve the black box function interval? So this is the second ongoing and a future work. So to conclude, in this work, I propose GoUCB algorithm, and this is the first work to solve the global optimization with a parametric function approximation. Here, the parametric function is pretty general. It can be the linear function. If it is a linear function, then the problem reduced to the linear banded problem. And then but more generally, the parametric function can also be a quadratic function, and even can be a deep neural network. And in this work, I'm not assuming the Gaussian process ends in the Bayesian optimization, so it does not suffer from the curse of dimensionality in theory. And also, my cumulative regret bound is at the order of the square root of t, and that it does not depend on the input dimension, the small d. How can I achieve this? Because I'm using another deep neural network, another parametric function to approximate the original function. So the cumulative regret bound does not depend on the input dimension. And I'd like to acknowledge the algorithm design itself is inspired by the linear UCB, which is a paper appears in the NeurIPS 2011, which is a very classical paper, I should say. But here the difference is that since I am dealing with more general nonlinear parametric function, so I incur a lot of technical challenge, and I have some technical novelty, which comes from the higher order residual term after the first order expansion. I mean, here the first order expansion means that I am using the first order approximation so that the algorithm behaves like a linear function, but I do have some higher order residual terms that need to be carefully dealt with. So this is the main contribution parts. I am able to deal with a nonlinear function approximation. and also the nonlinear function global optimization. And there are two ongoing and future work that I'd like to pursue. The first is misspecified GoUCP, and also the multi-fidelity GoUCP. Feel free to talk to me online or offline, and I'd like to happy to collaborate on this project. Okay, so this is the end of my talk. Thank you, everyone. And right now, I'm happy to take questions. Thank you.
Thank you very much for Chong's great talk. Hi, audience. If you have any questions, please, you can directly open your mic to ask. Before that, I personally have a questions, kind of things. I'm working on the adversarial robustness. There's one method called a black box adversarial attack. Basically, it's quite similar to the black box optimization to find the input data, which is very near to the original data, but can make the loss of the neural network highest. So it's very similar to this. I think your black box method can directly apply to this scenario to designing the black box adversarial attack. What do you think?
Could you describe more about like the black box attack? What is the problem set about that?
Yeah, for example, the input is more like an image, right? So therefore, the image is high dimensional, like 1,000 dimension is the input. Then go through the network make a prediction. I want to this input to be similar to the original input, but slightly modified. Then the network will make a very wrong prediction on the slightly modified input. We call this adversarial example. But in this case, we don't know the parameters of the deep neural network in the black box setting. So we want to find this input that make this network predict wrongly, as wrong as possible. So what do you think?
Sure. I think the deep neural network in this case can be also understand like the black box. Yes, of course. And you have different inputs, and then you can have like different. I mean, the output, right? You said that by inputting two similar images, and then the output can be very, very different, right? Yes. So it's just like puts a very strict limitation on the function itself. I mean, usually when we do the global optimization, people usually assume the smoothness assumption, and which means that here is x1 and x2, and x1 and x2 they are not too different, and then the output should be not too different, right? So yeah, I think if you want to use a black box optimization technique to solve the black box adversarial attack problem, then you need to get rid of the smoothness assumption, and it can be quite a challenge, but quite interesting, I should say.
Yeah, indeed. Because the reason I think because the adversarial example happens in the deep neural network is just because there are no such smoothness assumption in the network. That there are no such Lipschitz bound on the input to the output.
Exactly.
That will be, I guess, in this way, maybe, the current your method may not naively apply to the black box attacks, maybe new versions. So then I have a follow-up question.
Sure.
We know that sometimes we may not totally don't understand the model, the function. For example, we may have some auxiliary information toward this black box function because we want to optimize it to get a point that is make this function highest. We have some auxiliary information. So what do you think whether we can incorporate some auxiliary information into the black box optimization? Maybe we can significantly help and yeah, reduce this problem. What do you think?
Sure. That's a very good point. And I'd like to say there is a line of research that is happening right now. It is called gray box optimization, and one of the leading researcher is Peter Fraser, Professor Peter Fraser in the Cornell University, and he has an excellent survey paper that maybe you are interested to read that. The key idea of the gray box optimization is that it is discussed the different kind of auxiliary information that we may have. For example, I have some knowledge of the function structure. And for a detailed example, I should say, for example, the vaccine development, it has 3 phases, right? I have the lab test, the animal test, and then the human test. I have knowledge of the function structure. And then doing the optimization over this whole process, this is a gray box to me. It is not a totally black box. So there are many ways that we can incorporate the knowledge and the new information. And for example, in some case, we may have some knowledge about the gradient, and the first order gradient is able to help us speed up the optimization process at some point. And as long as I can find a very good local region, and then I can run the gradient information. Yeah.
I see. Thank you. So yeah, I think so. Yeah, depends on the application you work on. You may have different auxiliary information. The different auxiliary information may help differently. So indeed, it's a complex question. Okay. Then I have no further questions. Thank you very much. So if others have more questions, they can send you an email to ask you directly. I believe you have write your email here. All right. Thank you again. Thank you very much for today's talk. Now this is the end of today's seminar. Thank you for coming.
Thank you.